Okay, so yesterday we derived four Maxwell equations in differential form, which we already know in integral form. Those equations were written in differential form. Let me write those differential equations for you here again. First, Maxwell's equation, differential in differential form, is about divergence of electric field, which is equals to rho volume charge density divided by permittivity of free space. I'm writing Maxwell equations for free space when medium is vacuum or it is air free space medium. Then we have second Maxwell's equation, which is about divergence of magnetic field, and divergence of magnetic field is this is always zero. Then curl of, which is Faraday's second law of electromagnetic induction. Differential form में we can write it like it is minus d by dt of magnetic field B. Then fourth is Ampere's law, which is about curl of magnetic field. It is unmodified form is only J, but when we modify it, it is this conduction current density. This is, let me write J subscript C. C stands for conduction current here. Plus I have one more term, and that is JD. It is in case we have what? We have uh, displacement current. This was introduced. This was introduced by Maxwell, and this becomes consistent when we add this term, that is displacement current density here, which is epsilon naught times d by dt of E. So these are my four Maxwell equations which we have derived yesterday. Or as we know, I can also write this in this form. This is Jc plus epsilon naught times E is electric displacement vector D divided by dt. And let me introduce this. D is what? It is electric field, resultant electric field in any dielectric medium. So it is epsilon naught E plus there is one more contribution to this. This is due to polarization of that dielectric medium. So resultant electric field in any medium, dielectric medium, is field in free space plus there is contribution due to polarization or polarized or charges which are developed in that dielectric due to polarization, and that gives you another field. And in case this polarization is zero, for example we have vacuum, so no polarization is zero, then D is equals to epsilon naught times E. So we can say that we are using this because we are talking about free space here. So I can say that D is epsilon naught times E. There is no component to this field, or nothing is added to this field due to polarization. So these are my four Maxwell equations. And important is, as I said yesterday, that modification which was introduced by Maxwell. So we'll go into some more detail about that. Why this modification? This is about displacement current. He introduced concept of displacement current, and this displacement current, it modified the Ampere's law. There was inconsistency in this law earlier, and then that inconsistency was removed when we introduce displacement current. Then it becomes modified form. Okay, so okay, so we were saying that this modification in Ampere's law is important, and Maxwell added this term that is displacement current, and he said that displacement current is proportional to, this is not due to flow of charge carriers, but it is due to time varying electric field. Whenever there is time varying electric field in any region, in any space, then effect of that time varying electric field is it produces magnetic field. And it is like similar to what as conduction current is responsible for magnetic field, there this time varying electric field is responsible for magnetic field. So it is as if that there is some current, displacement current, which is producing magnetic field. So we write that magnetic field, or sorry, this displacement current, which is epsilon naught times d by dt of E, that is electric field. So this, sorry, d by dt of phi E. So phi E is, it is flux due to electric field. So in any region, when we say that E will vary, electric field varies with time. So electric flux linked with the with any area in that region will also vary, and that decides what is the magnitude of displacement current in that region. Let us try to predict magnitude of this displacement current for a case where we have a parallel plate capacitor. We have circular parallel plate capacitor. This is circular parallel plate capacitor. I know conduction current flows through the wire. This up to here, this is what this is conduction current. And here also we have what we have conduction current. When we complete the circuit, you can see that conduction current will flow. And due to this conduction current, there will be what? There will be charging of this these capacitor plates. Charge will grow on these capacitor plates, and charging and discharging of capacitor, you understand it is. So this is what we are interested in predicting. What is the amount of displacement current produced between the plates of the capacitor? Because here it is conduction, and here there will be timing electric field, because I know a charge will grow, and suppose that Q is the charge on the plates of the capacitor, and area of cross section of this plate is what it is, A. Then I can write electric field here, electric field between the plates, it is what it is, sigma divided by epsilon naught. This is, you know from your previous knowledge, that this electric field, resultant electric field due to both the plates, positive, negative, it is what it is, sigma divided by epsilon naught. Sigma is surface charge density on the plates. So I can write this is sigma is Q divided by A. A is the area of each plate. So this is surface charge density. So I can write, I put this here. So you can write electric field is Q divided by epsilon naught times A. And A is the area of cross section of this circular plate, which is, I can say, pi r square, where capital R is the radius of this plate. So I replace here this area by pi r square. So I can write electric field between the capacitor plates can be written like this. This is Q, charge on the capacitor plates, each capacitor plate, epsilon naught divided by epsilon naught pi square of radius of each plate. And what I said, we are interested in d by dt of phi, that is electric flux. I can draw any imaginary area here, and you can see this is my imaginary area. And what is the flux linked with that imaginary area? That will decide what? That will decide what is the magnitude of displacement current between the plates of the capacitor. Or I know flux is what it is. I can write it as epsilon naught times d by dt of integral E dot ds. This is what this is, electric flux. And this is not closed integral, this is open integral, because my plane surface is what it is, a plane surface or open surface. And as I said yesterday, we can interchange operation of these operators. I have operator, integral operator, and I have another operator, that is d by dt. Both these operators are linear operators. As these are linear operators, so they have property that we can interchange their operation. So as we can interchange their operation, so I can write this as, this is epsilon naught, and it is integral d by dt of E times ds or ds. So I require to estimate what is the magnitude of displacement current. You should know what is this, how electric field is changing with time. So d by dt of E, I have predicted that this is the electric field between the plates of the capacitor. So I can write, I can find what is the rate of change of this electric field. So d by dt of this is, I know what is here. It is epsilon is constant, pi is constant, r square is constant, this epsilon is constant. So it is only d by dt of charge is growing or it is decaying on the plates of the capacitor. So I can write it as d by dt of q. Then finally I can write that this d by dt of E is 1 over pi r square times epsilon naught, and this is nothing but, this is rate of flow of charge. This is what, this is rate of how charge is growing and how charge is decaying. So that is proportional to, or that is equal to conduction current. So I can write this is what, this is this, and let me see this again. ID is epsilon naught times, this is, I can take this out, I can write this as d by dt, and this is the integral of ds. And ds is what, it is part of this this open area here. So and flux between the plates of the capacitor, it is due to what, it is due to the area inside this imaginary area, which is equals to the area of these plates. So I can write this is epsilon naught times, I'll write what is d by dt of E, and here I have pi r square, and here I have EI divided by this expression, this is d by dt of E, I divided by pi r square epsilon naught. This is my displacement current. What is displacement current? It is this, it is. So I can see that pi r square, I square, I can cancel epsilon naught, epsilon naught. So ID is what it is, I. In magnitude, what I can say, in magnitude, displacement current is equal to conduction current between the plates, capacitor plates. That means if 1 ampere current is flowing, conduction current is flowing on the wires, and here also 1 ampere. So consistency of this current is what? This is 1 ampere current, no displacement current here. This is conduction, this is, there is no conduction current here, but displacement current is equal, due to this it is equals to 1 ampere as according to this. So that means there is 1 ampere current throughout this circuit. Okay, so this gives you that current is what, it is consistent in the circuit, and displacement current, magnitude of displacement current is equal to conduction current in case of when we have capacitor plates. So now I'm interested in doing what? I'm interested, as there is this displacement current, and I know from my Maxwell's equation 4 that both the currents, that is displacement current as well as conduction, displacement current as well as conduction, both are responsible for producing magnetic field. I have Ampere's law that was for conduction current, and I know that Ampere's law, it gives you that P dot dl. If I walk along a loop, okay, this is that loop where we have current carrying conductor here, which is producing magnetic field all around it. And if I walk along a loop, that is B dot dl, then I can find this B dot dl, which is equals to mu naught times I. This is Ampere's law. This is what we know, Ampere's law. And I can see that conduction current is producing what? Magnetic field. Now I have added one more term here, that is displacement current, and that is also producing magnetic field. And this displacement current, I can see where it is in the region where electric field is varying. I see this displacement current between the plates of the capacitor. So I'm interested in knowing how this displacement current is varying with with the distance or with position between the capacitor plates. So let me do what? Let me say, let me find magnetic field here due to displacement current. Magnetic field at this edge where distance from the axis is equals to r. This is radius of each capacitor plate. And I take another point here whose distance is more than r from the axis, so that I can see how magnetic field, what is the nature of magnetic field or how it varies with R inside or between the capacitor plates. Between two capacitor plates, if I move away from the center, then how magnetic field varies. I'm interested in knowing that variation, because I know what I know. If I have a current carrying conductor, I move away from this current carrying conductor, how magnetic field varies with R with distance from the current carrying conductor. I have that expression, and from unmodified form of Ampere's law, you can easily find this expression. I'm interested in finding magnetic field at this point, which is at r distance from the current carrying conductor. I draw Ampere's loop, and then I say that apply Ampere's law, that is V dot dl. Closed line integral of this is equals to mu naught times current threading through this loop, and I have attached plane surface to the loop, and this plane surface is penetrated by this current, so I say that it is mu naught times I. And I can simplify this because magnitude of this is B dot dl, and direction of B as well as dl, they are always same, so I can simply write it as B dl, and B is always same, all magnitude of B is same all along this loop. It is as per the symmetry of this loop. So I can say that this is B times integral, closed line integral of dl is mu naught times I, and closed line integral of this circular loop, I have assumed this as a circular loop, as there is no restriction as per Ampere's law that loop should be circular. It can be of any shape, but for my convenience or to do mathematics easily, I assume that this is a circular loop. Then I can write it as what it is, B times 2 pi r. R is this distance, and radius of this circular loop is equals to mu naught times I, and you easily predict that B is equals to mu naught. Let me multiply and divide by 2, so I can write this 2 pi as 4 pi, and this is then 2I divided by R. So this is magnetic field due to a current carrying conductor. Okay, we all know this, we have done this number of times, and we are convinced that this is how magnetic field varies as you move away from a current carrying conductor. Now, this is magnetic field due to due to conduction current, and now we have what we have, displacement current. And in case I have this system where we have capacitor plates, and I know that between the capacitor plates we have displacement current due to time varying electric field. So I'm interested in knowing how this magnetic field due to displacement current varies as I move away from the center of this capacitor plates. So for that, let me apply this again. Let me see that variation and how it is different from this. So to give you little idea what is displacement current. So for that, let me take 3 cases. Case 1 is when we say that observation point where we are interested in knowing the magnetic field is close to the center of the circular plates. This is case 1. Case 1 means when we have, this is my first circular plate, capacitor plate. I have another, these are parallel plates, capacitor plates. Okay, so here this is the center, and my first observation point is this, which is at distance RA. Let me call this point as A point, small a. So distance is what R is equals to RA. Magnetic field here is denoted by BA, and I know what I know that B is equal to BA, and I know what this RA is, what it is less than a radius of the capacitor plates. So this is my case one. This distance is what it is R, that is radius of capacitor plate. I take another case, that is when I'll be finding magnetic field at this point. This is B point at the edge. I can say when R is equals to RA, then B is equals to B subscript small b, and R B is exactly equal to what it is equals to R, radius of the capacitor plates. Let me take case 3 when I have point C. I'm interested in finding magnetic field there. So this R is equals to RC. This distance is not RC. And then magnetic field is denoted by BC there. And RC is greater than radius of the capacitor plates. Okay, so if we apply Ampere's law, now we have modified form of Ampere's law. And this modified form of Ampere's law will give you what? It is magnetic field at A point. So I can write closed line integral of, I draw Ampere's loop here. This is Ampere's loop. Okay, plane surface is attached to this Ampere's loop. And then it is dot dl, BA dot dl. This is equals to mu naught times, there is no conduction current here, but I have displacement current, so I can write it is epsilon naught times d by dt of E. This is displacement current. This is displacement current now. Okay, so and I can write this as this is BA. We have idea about these simplifications, so I can write this is integral closed in line integral of dl. It is part of dl is part of this loop, so I can write it as RA, 2 pi RA is equals to mu naught epsilon naught. What is d by dt of E? I know that, and write that expression here, and then it is what it is, flux linked with this loop, which is area of this loop. It is pi small r a square. Okay, and what is expression for d by dt of E? It is this what we have written here. This is d by dt of E. It is I conduction current, or it is equivalent to current. So this is divided by pi r square epsilon naught. I see I can write now BA, and before that you can cancel this with this. You can cancel pi with pi. So and then BA can be written as BA is mu naught times I divided by, let me write this 2 pi in the denominator. This r square is there. I can cancel this r a with square of ra, so I'll be left with ra here. So it will be this. So this means what? This means that magnetic field at a point, or for all points in whose distance is less than radius of the capacitor plates, is directly proportional to Ra. Okay, this is for all points whose distance is less than R, capital R. Then let us find in the same way we can discuss case 2, where I said that point is at this place, it is point is B, And then I can again apply this Ampere's law. I draw Ampere's loop now. This is my Ampere's loop. And radius of Ampere's loop is exactly equal to radius of the capacitor plates. So I can write it as B subscript B dot dl. dl is part of this circular loop, is equals to mu naught epsilon naught, and I'll be writing expression for this displacement current, which is I divided by 4 pi r square epsilon naught. And here I have what? I have integral ds, and this integral ds is what it is now, pi r square flux linked with this big loop of radius r is this times this. So it is pi r square here. And on the left hand side, you can see that it is B subscript B, and this is part of this loop. So circumference of this loop is the closed line integral of dl. So I can write it as capital R. So it is mu naught epsilon naught. Pi r square gets cancelled with this pi r square. So epsilon naught also gets cancelled with this epsilon naught. So I have this, only this. And then B subscript B is mu naught I divided by 2 pi r. This is magnetic field at this point at the edge. Okay, then third case is I can write Ampere's law to find magnetic field at C point, and C is outside the capacitor plates, or you can say distance of C from the center is greater than the radius of the capacitor plates. Okay, so you apply Ampere's law, and then you see what is the expression and how this expression is different from the earlier two expressions. And then finally we can do what? We can plot a graph, or we can see how B varies. We can plot that variation of B magnetic field with distance from the center of capacitor plates. So for that, let me apply Ampere's law again. Case 3 is when this is closed line integral B subscript C dot dl. Ampere's loop is what it is. This is this big. Okay, radius of this Ampere's loop is RC now. So I can write this as mu naught epsilon naught. Again, d by dt of E is I divided by pi capital R square epsilon naught. And here we have this integral ds, but flux is linked with only this part. There is no electric field outside the capacitor plates. So this part, there is no flux is linked with this loop. So I can say it is only pi R square, capital R square. So then I can write left hand side, that is B times 2 pi R C, and I can see on this side I can cancel pi R square with pi R square, epsilon naught with epsilon naught, so I'm left with mu naught times I, or I can write B is equals to mu naught times I divided by 2 pi R C, where RC is greater than R. So for all the distances which are greater than R, expression for magnetic field is this, and for all the distances which are less than R, we have this expression, and for distance which is exactly equal to R, we have this expression. So if I see all these three and I try to plot a graph of magnetic field, so magnetic field varies with R, As we move away, you see up to R equals to R, this or up to R equals to R, there is, it is directly proportional to magnetic field is directly proportional to R. So it is straight line graph up to this, and after that we see, and at this, that is R equals to R, we have this expression for magnetic field. You can say that this value of magnetic field is mu naught I divided by 2 pi R, that is maximum value of magnetic field, and after that it is inversely proportional to R. Magnetic field varies inversely as R. You can plot it like this. So this is how magnetic field between the plates of capacitor due to displacement current. This is magnetic field, how it varies. So we can talk about consistency now. Consistency of Ampere's law. We said that Ampere's law was modified by Maxwell, and as it was modified by Maxwell, that modified form is better. That modified form is not inconsistent like Ampere's law. And what was inconsistency in Ampere's law? It is related to, you can see, finding magnetic field. It cannot find magnetic field if we have capacitor plates. I have capacitor plates here, and I'm interested in finding magnetic field at a point, and then I'm also interested in finding, let me draw it like this, these are capacitor plates, and I'm interested in finding magnetic field at a point. I'm also interested in finding magnetic field at B point. So this is A point and this is B point. If I do not have modified form of Ampere's law, then there is no current between the plates of capacitor. But here we have conduction current which is flowing on this wire, and I draw Ampere's loop here of radius equal to distance of A from the current carrying wire, and I apply Ampere's law, that is B dot or B times 2 pi distance of A from the axis is equals to mu naught times, because current is threading this loop plane surface is attached to this loop. So it is, that plane surface is penetrated by current I, so I can write it like this, or I can write that magnetic field at A point is equals to mu naught times I divided by 2 pi R. Okay, but what about magnetic field at B point? If I again draw Ampere's loop here, and plane surface is attached to this Ampere's loop, so no conduction current threads the Ampere's loop, then I say that magnetic field at this point B, it is 2 pi R loop, circumference of loop, equals to mu naught times, as current is 0, conduction current is 0, so it gives you 0. Okay, and if we make it more clear, let us say that this is point A, and I'm interested in finding magnetic field at this point. I draw Ampere's loop. I attach plane surface to this Ampere's loop. I can apply Ampere's law to find magnetic field at A point, and this magnetic field at A point according to Ampere's law can be predicted from this. It is B times 2 pi R equals to mu naught times I, or we can write this B subscript A is equals to mu naught I divided by 2 pi R. Okay, this is fine. This is as we have done earlier. But if I attach, because according to Ampere's law, you can attach any surface to the Ampere's loop. It is not that we have to attach only plane surface to the Ampere's loop. Let me draw some other, attach some other surface, and this is what it is, the surface attached to the Ampere's loop. This is my loop, and to this loop, surface attached is not a plane surface, but it is this surface of this shape. And you can see this is like what? It is like a hollow bag. Okay, and the surface of this is what it is here. This is the surface. This is the surface. And this is hollow from this side. So plane surface means what it is, like a disk. You have surface here, but in this it is not, surface is not here. It is what it is, this is the surface. And you can see if I try to apply Ampere's law to find magnetic field at the same point A, which I know is this, but about if we attach different surface, apply the same Ampere's law, then we see that this is what this is, mu naught times current I, and let me write it is again 2 pi r, because loop is of the same size, only surface attached is different. So it is mu naught times, as no current is threading, conduction current is threading this, or is penetrating this surface, okay, surface of attached to this loop. So B at A comes out to be 0. This is contradictory. If we apply Ampere's law with this surface, we get magnetic field non-zero. But if we attach different surface to the Ampere's loop, which is allowed as per Ampere's law, then we get what we get. Magnetic field is equals to 0 at the same point, which is not possible. Magnetic field at the same point, doing different calculations, it should not be different, as both the calculations are valid. So we are getting different results. So this is what this is, inconsistency with Ampere's law. That's why it was modified by Maxwell, and he introduced that here what is threading, it is displacement current is threading. So then, and as I said that magnitude दोनों का बराबर होता है, displacement current and conduction current. So then this will also be non-zero. You can write then this is ID now. This is ID. Here it is IC. When we have plane surface, then you see that this is the surface. It is outside the plates of capacitor. So only we have conduction current outside. So this is IC, which is equals to I. And this is ID. This is also equals to I. So you can find what you will get the same result, that magnetic field is again mu naught I divided by 2 pi r. So this makes it consistent. When we introduce displacement current, that gives sense to Ampere's law, and this remains valid, that you can attach any surface to the Ampere's loop, and attaching different surfaces to the Ampere's loop, there's no effect on your result. Your result remains what it remains, same. So this is discussion about displacement current, then modification of Ampere's law, which is very important, and it was modified, and it is now called Maxwell-Ampere's law. Now we can do what we have: electric field, we have magnetic field, and these are fields which are varying. We can find divergence of both the fields. Divergence of electric field, divergence of magnetic field, curl of electric field, curl of magnetic field, and these are the equations, Maxwell's equations, which are giving all these operations. So you see that according to these Maxwell's equations, we do unification. We say that changing magnetic field is this. It is not only charge which produces electric field, it is what it is also time varying electric field which can produce electric field, magnetic field which can produce electric field. Same is that it is not only the dipole, magnetic dipole, which produces magnetic field, but it is with that it is what it is, time varying electric field and conduction current, both are responsible for magnetic field. So that means electric field and magnetic field, these are coupled fields. Whenever we have time varying electric field, you'll get magnetic field. This is time varying magnetic field. That's why time derivative of this is some non-zero term. If it comes out to be zero, curl of E is zero, that means you do not have time varying electric field, and then it is what it is. Then it is static field. Okay, then it is what it is, static field. So we are talking about time varying fields. So in electromagnetic waves, we have time varying fields, we have time varying electric field, we have time varying magnetic field, and as we have time varying electric field, that will result in magnetic field and magnetic field. So they are coupled, and you cannot think of one without the other. You cannot think of electric field without magnetic field, because as per these relations, whenever you have B field and it is time varying, E will always be there. Same is true other way around. When you have time varying electric field, you cannot say that there will be no magnetic field. So these are coupled fields in electromagnetic waves. It is the best example is electromagnetic waves. In electromagnetic waves, you can see both the fields E as well as B, and they are perpendicular to each other. And if we see polarized light, then you can see only one component of E and one component of B, and both are perpendicular to the propagation of that electromagnetic wave. But unpolarized light, if we see, then you'll be able to see all the components, and there will be infinite number of components of E and corresponding components for B, and they move in all the directions, all the possible directions. Okay, so with this, let us try to derive, because we are talking about electromagnetic waves now, EM waves. I'm interested in writing mathematical description of this electromagnetic wave. If I have any wave, it is like wave on a rope. This is what this is. Wave is produced on a rope. Then I know that this is suppose along x direction. It is displacement. This is what I can write to y. Y is displacement of these rope particles or rope molecules. So this is function of x and t. It varies with time. So this is wave function for this wave. And E and B are wave functions for electric and magnetic field. This is one dimensional case I'm talking about. This is propagation is only along this direction, that is x direction. And I can write this, and I know time it varies with this, y varies with x as well as with t, and those derivatives, I can find derivative of y with respect to x as well as derivative of y with respect to t, and how those derivatives are related. That is sort of that is equation of motion for this wave. So I can write, as we do it in case of moving particle, we write equation of motion, which is Newton's second law, F equals to ma. Similarly, we can write equation of motion for these waves to study characteristics of these waves. So I have a simple wave, and I can write wave equation for this. It is d square over d x square of y is equals to 1 over v square times d square over dt square of y. So this is for wave equation for wave on a rope, and this is one dimensional wave, which is only x direction is the propagation direction. So this is double derivative of the wave function with respect to the position, and this is double derivative of the same wave function with respect to x, and this is velocity of this wave. V here is what it is, velocity with which wave is propagating, or with which disturbance energy is propagating along the x-axis. So why I'm giving you this description, because we'll be writing similar wave equation for electromagnetic waves. And you can write, this is general wave equation for any wave, because if I replace y here, y is the wave function, I replace y by E, that is electric field component of electromagnetic wave, then it becomes wave equation for E component of electromagnetic wave. If I replace y by B, that is magnetic field, so this will give you what it will give you, magnetic field component of electromagnetic wave, or wave equation for electromagnetic component of wave, electromagnetic wave. So, and in this is as I said, that one dimensional case where direction of propagation is only x, And three-dimensional, you know, this is derivative. What derivative it is? Second, this is operator d square over dx square, and this can be replaced by three-dimensional operator del square. Operation of this on y is equals to 1 over v square, and then I have d square over dt square of y. This is what this is, three-dimensional wave equation. Okay, and if I replace this y by E field, then it becomes wave equation for E component of electromagnetic waves. So I'll be deriving this. I'll be deriving this wave equation for E as well as for B components. And as I said that writing Maxwell's equations from integral form into differential form will help us in doing simplifying our mathematics. So that you will see here, the best example of that is this. We can derive this wave equation. We cannot derive these wave equations using integral form of Maxwell's equations, but we can use now differential. I have Maxwell equations in differential form, and I can use this form to write wave equation for electromagnetic waves. It is very simple to do it. We do what we use this equation. This is curl of E is equals to negative of d by dt of B. If I take curl of this equation, take curl, you know curl operation now. So taking curl of this means what? Curl of this, that is curl of E, is equals to curl of right hand side, which is minus d by dt of B. And I have, this is my you have formula identity for this. I write this curl of any vector is what is gradient of divergence of that vector minus del square E, divergence of that, which can be written as del square E is equals to, I can again interchange operation of these operators. This is del operator and this is d by dt operator. So I can write minus d by dt. Let me operate with this del operator first on B, and then I'll be doing d by dt of this, or I'll be operating with this operator. Okay, and now this is what this is for. Let me write, these are Maxwell's equations for any medium. I can write Maxwell's equations for free space, for vacuum, you can say, for vacuum. And when I write Maxwell's equations for vacuum, I have to make some changes in these Maxwell's equations. And if I have vacuum, means there is nothing is present, rho is zero, charge density, no charge, no density, no charge density. Displacement current will be there, but there will be no conduction current and there will be no conduction current density. So these two will be zero. No charge is flowing, no conduction current, and no conduction current density. So with these changes, I can rewrite my Maxwell's equations for free space. So my first Maxwell's equation, it will become divergence of E, which was earlier rho divided by epsilon naught, and now rho is zero, so it is this. My Maxwell's equation number 2 will remain as it is, no change in this. No change in Maxwell's equation number 3, but I can write it as minus d by dt of B can be written as mu naught times H for free space. This is for free space, vacuum. And I can take that mu naught here. Let me write only this as d by dt of H. This is d by dt of H. And I can also write my fourth this Maxwell's equation. This is zero now, conduction current density is zero, but I can write for free space, as I said earlier, this d displacement vector, which is epsilon naught E plus P polarization vector, as we have free space, no polarization. So it is epsilon naught times E. So I use that here. So it is epsilon naught times E d by dt of E. So these are my four Maxwell's equations for vacuum. So when I take curl of this equation, okay, and we are using free space, so we can say that this B can be written as, now this B is mu naught times H. So let me write mu naught times H here. Okay, and this is mu naught and curl of H. And this is zero. Why this is zero? Because I know now this divergence of E is zero. Divergence of E is zero. I'm left with negative of del square E on left hand side. And on right hand side, I have negative of mu naught d by dt of curl of H. And what I know curl of H is from my equations, curl of H is this. So I can write minus del square E is equals to minus mu naught d by dt, and curl of H is this. So I can write mu naught d by dt of E. I can cancel negative sign with negative sign. So I have del square E is equals to uh, epsilon naught mu naught. And if I operate with this operator on this is double derivative of E with respect to time. And this looks like this equation which I was trying to write. This is del square of E is some parameter here times double derivative of E with respect to t. As I said earlier, this is nothing but this is square of velocity. So if I compare it with, so I can write that 1 over v square is equals to this, that is epsilon naught mu naught, or we can say that v is 1 over under root mu naught epsilon naught. So velocity for electromagnetic waves in free space is given by 1 over under root epsilon naught mu naught. And I know values for both these constants. Epsilon naught is 8.85 into 10 raised to the power minus 12. Mu naught is 4 pi into 10 raised to the power minus 7 with some units. If I put those values here, so I get what? I get exactly what is the velocity of light in free space. So it is some 2.99 whatever. So I'm writing straight away as this. It is what? It is 3 into 10 raised to the power 8 meters per second. Similarly, you can write, this is one component of electromagnetic wave, and that is E component. Electric field component varies in electromagnetic wave, because you know this is how we see electromagnetic wave. It is having both the fields, electric and magnetic. Both are varying with space as well as time, space coordinates as well as time. And polarized electromagnetic wave you see like this. This you can see, this is electric field component of electromagnetic wave traveling along this x direction, and this is what this is magnetic field component. Both are varying. So you draw magnetic field like this, and this is what this is electric field perpendicular. One is along this y direction, other is along z direction. Okay, and this is direction of propagation. So I have written for this wave, I have written wave equation. This is suppose electric field. So this is this. Similar wave equation I can write for this component of electric field, electromagnetic field, and that I again use Maxwell equations. And अभी हमने इसका कर्ल लिया था अभी, है ना, taking curl of equation number 3 on both the sides, we get this result. Now we take curl of equation number 4 on both the sides, so curl of this and curl of the whole part here. But again, as we know that curl, we should write it here, curl of again we know that this is free space. As this is free space, means no displacement current and no conduction current and no charge density. So taking this is that Maxwell's fourth equation. We take this is Maxwell's fourth equation, and we are taking curl of this Maxwell's fourth equation on both the sides. Again, using that vector identity, we can write this as this. This is gradient of divergence of H minus divergence of H, which is del square H, is equals to, I can interchange operation of these operators. So I write this epsilon naught d by dt. First I operate with del operator on E, and I get curl of E from my Maxwell's equations, and I know what it is. It is mu naught times d by dt of H. Okay, and rest is what it is, mu naught and derivative. So you can see that I can take epsilon naught mu naught out and double derivative of H with respect to this. And on right hand side, this is equals to 0 from that divergence of B is equals to 0. So B can be replaced by mu naught H. So divergence of H is also 0. So I'm left with this thing, and that gives you वो negative sign जो यहाँ इसका आना था, that gets cancelled with this negative sign, and you get what? You get similar equation as a wave equation as we have derived for electric field component. From here as well, you can find that this V, which is 1 over under root mu naught epsilon naught, is equals to what it is, putting these values here. It is 3 into 10 raised to the power 8 meter per second. Okay, so this is how these Maxwell equations are helpful in predicting, in writing wave equation, and then in predicting velocity of these electromagnetic waves in free space. And you have done these electromagnetic waves in earlier classes as well, and you are aware about properties of electromagnetic waves. But if you are not aware, you go through it, and I'll also give you a brief idea about properties of electromagnetic waves. And then next time we will start with the new topic. We will see that how these electromagnetic waves, they propagate through different media. It is like in free space, and then is the effect of these electromagnetic waves when they move through any conducting medium or in any dielectric medium. Okay, so okay, let us end today's lecture here only. If you have anything, any queries, you can ask, and rest of you can hang up.
Thank you, sir.
Okay.